Hello student, good morning. I am Dr. K, Professor of Chemistry. Last class I have started a chemical equilibrium and I have given background for chemical equilibrium. Now I am going ahead. I am giving next example of physical process or physical equilibrium. Okay. Then it's another example is liquid vapor equilibrium. Liquid vapor equilibrium. And here you can understand by some experiment. Okay. Equilibrium concept you can understand its concept you can understand better by example, okay, by experiment. This I am talking about liquid vapor equilibrium. This equilibrium can be better understood if we consider the example of a transparent box carrying a U tube with mercury manometer. Okay, with mercury manometer. Manometer measure the pressure. This question is asked. Okay, in that first you keep a drying agent. You should know that some example of drying agent. Then example of drying agent is anhydrous calcium chloride. Anhydrous calcium chloride. There are two types of calcium chloride. First, hydrated means calcium chloride may have some water molecules attached. Then that is called calcium hydrated. When calcium chloride does not have water molecules, then it is called anhydrous. Anhydrous. It has capacity to absorb the water. Second example of drying agent is phosphorus pentaoxide P2O5. P2O5. It is also called drying agent. Okay. Then now to understand liquid vapor equilibrium, you can understand it by example of transparent box carrying a U tube with mercury, okay, manometer. In that, suppose first you have kept drying agent. Drying agent in that box you have kept, just it should be dry. Either drying agent may be anhydrous calcium chloride or phosphorus pentoxide, anyone. So that box should be dried. After that, you can keep in a petri dish or watch glass some water, liquid water you can keep. Okay. Then now after that a process will start. In petri dish or watch glass you take some water. Okay. After removing the drying agent, a watch glass containing water is quickly placed inside the box. Okay. Then what will happen? It will be observed that the mercury level in the right limb of the manometer slowly increases. Means pressure will increase and finally attains a constant value. Then what happened here? That water evaporated. Water molecules evaporated. That's why pressure increased. That's why manometer will show increased pressure, and after some time it will be constant. Okay. That constant, it will show the constant value. It has increased, pressure increased, and after that it became constant. That is, the pressure inside the box increases and reaches a constant value. Also, the volume of water in the watch glass decreases. Obviously, because water molecules evaporated, then their quantity will decrease, volume will decrease. Initially, there was no water vapor. In the box, initially there was no water vapor. Or very less, because already you have made it dried by keeping the this calcium chloride, and later on that calcium chloride, when it became dry, you have removed. After that you have kept the water, means on watch glass you have water. After drying the this you have kept, you have removed the these things, calcium chloride you have removed. That's why in the beginning no water vapor was there, but now in the box water vapor developed due to the water of, you can say, water you have kept in watch glass. Due to that, initially there was no water vapor, or you can tell very negligible inside the box. Okay, as water evaporated, the pressure in the box increased due to addition of water molecules into the gaseous phase inside the box. See how evaporation takes place. Now you have understood. Here, the rate of evaporation is constant. Okay. However, the rate of increase in pressure decreases with time due to condensation of vapor into water. After some time, you will feel that now vapor, that pressure is decreasing, because that vapor is coming back to the liquid water. Okay, due to the condensation of vapor into water. Finally, it leads to an equilibrium condition where there is no net evaporation. Now no evaporation, no condensation, no evaporation. Okay, this process will continue. Means that time it became a constant. Okay, no condensation, no evaporation. But this situation is called equilibrium. This implies that a number of water molecules from the gaseous state into the liquid state also increases till the equilibrium is attained. And when equilibrium will attain, means I told you, then both will be going on. Means evaporation will be going on, and at same time condensation will also continue. Then evaporation, condensation, condensation. In equilibrium state, it will be there. That will not stop. Okay. After getting equilibrium, both process will be there. Then now that you can write this these things, this equilibrium you can mention like that: H2O liquid, sign of equilibrium, H2O vapor. H2O liquid, sign of equilibrium, H2O vapor means gas is liquid is converting to vapor, or vapor is converting to liquid, means sign of equilibrium, means double half arrow, double half arrow. That is a sign of equilibrium. At equilibrium, the pressure exerted by water molecules at a given temperature remains constant. Okay, already I have told you. At equilibrium, the pressure exerted by water molecules at a given temperature remains constant and is called the equilibrium vapor pressure of water. Okay. Vapor pressure of water increases with temperature. Obviously, if you will increase. If you will warm the water, then it will vaporize more, then pressure will be more. That's why vapor pressure of water increases with temperature. If the above experiment is related with methyl alcohol, again interesting things you can see. If the above experiment is repeated with methyl alcohol, acetone and ether, then what will happen? It is observed that different liquids have different equilibrium vapor. Different liquids have different equilibrium vapor pressure at the same temperature. Temperature is same, but vapor pressures are different. And the liquids which has a higher vapor pressure and the liquid which has a higher vapor pressure is more volatile and has a lower boiling point. More vapor pressure means less boiling point. Okay. If we expose 3 watch glasses containing separately 1 ml each of acetone, ethyl alcohol and water. Now again what you can do, if we expose 3 watch glasses containing separately 1 ml of acetone you keep in one, other you keep 1 ml ethyl alcohol, and third one you keep, third one watch glass 1 ml water you can keep. Okay, to the atmosphere. Now what you have done, that is in a container, closed container. Okay, now suppose you have kept in open, then what will happen? If we expose these watch glasses containing separately 1 ml each of acetone, ethyl alcohol and water to atmosphere and repeat the experiment with different volume of the liquids in a warmer room, it is observed that in all such cases the liquid eventually disappears and the time taken for complete evaporation depends on first, the nature of the liquid, second, the amount of the liquid, and third, the temperature. Okay, this all will evaporate, but time taken will be different. Means this evaporation, time of evaporation for complete evaporation depends upon the nature of the liquid, what type of liquid is there. Second, amount of liquid is more or less. If more liquid, it will take more time, less liquid, less time. And third, the temperature. If temperature is more, it will evaporate fast. If temperature is less, it will evaporate less. When the watch glass is open to the atmosphere, the rate of evaporation remains constant, but the molecules are you can say dispersed into the large volume of the room. As a consequence, the rate of condensation from the vapor to liquid state is much less than the rate of evaporation, because it is opened and all went to the atmosphere, in the room spread, but that's why it is not coming back, because it is opened, pressure difference is there. That's why they went to the atmosphere and it will not come back, means there will be no evaporation, no equilibrium, okay, because all you can say very less vapor will return, very less. Okay, this you should understand. Condensation will be very less. Okay, consequence that rate of condensation from the vapor to liquid state is much less than the rate of evaporation. These are open system. Why it happened? Because these are open system and it is not possible to reach equilibrium in an open system. Okay, Water and water vapors are water and water vapors. Okay. Water and water vapors are in equilibrium position at atmospheric pressure. Atmospheric pressure means 1.013 var. 1.013 var. Okay, that is called atmospheric pressure. Both are different. 1 atm and this both are different. Water and water vapors are in equilibrium at what condition? Then pressure should be 1.013 var and the temperature should be 100 degrees centigrade in a closed vessel. In a closed vessel, if pressure is 1.013 var and temperature is 100 degree, only then they will be in equilibrium. This is the condition. The boiling point of water is 100 degrees centigrade. Boiling point of water is 100 degrees centigrade. Okay, at 1.013 bar pressure. For any pure liquid at 1 atmospheric pressure, the temperature at which the liquid and vapors are at equilibrium is called normal boiling point. What is the boiling point? Then you can say that temperature at which the liquid and its vapor are at equilibrium is called normal boiling point of the liquid, and that time pressure should be 1.013 bar. Okay, boiling point of a liquid depends upon the atmospheric pressure. If it depends on the altitude means height. It depends on the altitude of the place. At high altitude means at a height like a mountain. At height altitude, the boiling point decreases because at hill pressure will be less. That's why water will boil soon. Okay. I have told you about now by experiment I have told about the liquid vapor equilibria. Same process it will apply everywhere. Same process will apply. Okay, during phase transition. Now next example I am telling you solid vapor equilibria. Solid vapor equilibria. Then what is the example of solid vapor equilibria? Then here two examples are there. Okay, first you can say iodine. Solid iodine, if you will keep in a room, then you will find its vapor is coming an entire room or entire container. Suppose in a container, closed container, you have kept solid iodine, I2, solid, then you will find after some times that in the container violet vapor is spread. Okay, then now see how solid is converting into vapor, violet vapor, and after that it will be constant, and again after that it will decrease. It will begin to decrease and equilibrium will take place. Means violet vapor of iodine, again it will convert to solid. Solid means solid to vapor, vapor to solid, solid to vapor, vapor to solid. This equilibrium will take place. Okay, this is the example of solid vapor equilibrium. Then iodine is the example. I2, iodine solid, sign of equilibrium, and I2 vapor. You can write I2 solid, after that sign of equilibrium, and I2 vapor. Other example is a camphor. Camphor means ammonium chloride. Ammonium chloride, that solid. Ammonium chloride, that is a camphor solid, it will convert to camphor vapor. Camphor vapor. Okay, means solid, camphor, solid, sign of equilibrium, and then you can write camphor vapor. Vapor. Okay, camphor is called as a you can say during puja time, na kapur you are using white color kapur, that is actually ammonium chloride. Chemical name is ammonium chloride. That you can see after burning it is converting to vapor. But because it is open, it is in open space, that's why it will not come back. But vapor will not come back. There will be no equilibrium because it is in open space. But same thing we will do in a container, closed container, then that vapor will come back. Then now second example I have given, camphor, that is ammonium chloride solid, that will convert to ammonium chloride vapor. Okay, then ammonium chloride, between the ammonium chloride solid and ammonium chloride vapor, you can write sign of equilibrium. Okay, then this I have told about the solid vapor equilibrium. Okay, third best example I am telling you, these things all are actually physical process. What I am telling you now, all are physical process, not chemical, physical. Then now you can see next example, solid or gases in liquids. Solid in liquids, and next example will be, I will discuss that gas in liquid. Okay, then solid in liquids, its best example is that sugar solution. Suppose water you have taken, in water you have added more sugar, then it will dissolve. But after that it will stop dissolving. It will not dissolve. That situation is called saturated. If water is there and you have added slowly, you can say sugar, then it will dissolve, it will dissolve. And because you are adding slowly sugar. But at the time, a time will come when it will not dissolve. Okay, it will settle, sugar will settle down. That is called saturated solution. But when you will heat the solution, then that also it will dissolve. Which was not dissolving, that also will dissolve. Even again if you will add the, you can say, sugar, again it will dissolve. Okay, means if you increase the temperature, solubility will increase. So more and more sugar will dissolve. Now, after that, if you will try to cool it, means if you will not it, then slowly automatically it will come to the room temperature. Then excess sugar will come out in the form of crystal. By the process of crystallization. If you will leave it at the room temperature, then slowly it will cool. It will become cool and at the room temperature, or as the temperature will decrease, that sugar will begin to come out. That is called crystallization. And sugar which is coming out, that will be pure sugar, that will come out. Okay, then this is the situation where you can understand that how solid and liquids, solid in liquids are in equilibrium. Okay, means they will, excess salt will come out. Then when it will reach to the room temperature, that time you will find then now solid is coming into the solution just at the boundary, liquid is there, solution, then from that solution and solid equilibrium will be there. Means from the solution, it is sugar is going outside, and same time sugar is returning to the solution. means from the solution solid is forming, from the solid again it is coming back to the solution. Then there one equilibrium will take place. That is called solid in liquids. Solid in liquids. At a higher temperature, sugar crystals separates out. If we cool the syrup, that is a solution is also called syrup. Okay. Then at a higher temperature, sugar crystal separates out if we cool the syrup to the room temperature. We call it a saturated solution. When no more of solute can be dissolved in it at a given temperature, okay, the concentration of the solute in a solution depends upon the temperature. Already I told you. If a saturated solution, in a saturated solution, a dynamic equilibrium exists between the solute molecule in the solid state and the solution. Sugar means you can write like this: sugar solution. If you want to write this equation, then you can write sugar solution, sign of equilibrium, sugar solid. Sugar solution, in bracket solution, write sugar solution, sign of equilibrium, and then sugar solid. And this time, and the rate of dissolution of sugar, that is equal to rate of crystallization of sugar. Okay. The rate of dissolution of sugar, that is equal to rate of crystallization of sugar. That time both rate will be equal. Rate of dissolution means dissolving, and rate of, you can say, these things, crystallization, both will be equal. Okay. Equally of the two rates are dynamic. Okay. Equality of the two rates and dynamic nature of equilibrium has been confirmed with the help of radioactive sugar. Again, if you want to know the very clear cut how they are about these things equilibrium, then you can understand by very good example that by radioactive sugar. Okay, if we drop some radioactive sugar into saturated solution of non-radioactive sugar, then after some time radioactivity is observed both in the solution and in the solid sugar. It means what? Sugar, it means sugar molecules are in equilibrium, they are in motion, they are in a dynamic. Okay, it's a very good example. Initially, there were no radioactive sugar. Initially, there were no radioactive sugar molecules in the solution, but due to dynamic nature of equilibrium, there is a exchange between the radioactive and non-radioactive sugar molecules between the two phases. This is the how will you prove? Then I have given the example. And one more thing, the ratio of radioactive to non-radioactive molecules in the solution increases till it attaining a constant value. Means it will change the ratio of radioactive to non-radioactive. The ratio of radioactive to non-radioactive molecules in the solution increases till it attain a constant value. Okay, this is the example of solids in liquids. Actually, you will not get many examples, but this type of process you will get. Organic chemistry, if you read the organic chemistry, then crystallization, if you will study, then copper sulfate also is the example. Copper sulfate in water, blue solution, there also same thing will happen. Okay, many examples are there, but organic and inorganic, you can say chemistry, if you will study crystallization, then you will find many examples like that. Now another, I can say, interesting example I am telling you, gases in liquids. Gases in liquids. You will think how gas in liquid. Then best example you can understand that in this things, cold drink bottle, if you will open, then as soon as you will open, then some gas will come out. Okay, that is actually carbon dioxide gas, because this carbon dioxide is filled in the bottle, in cold drink, that water is there, that cold drink, in that at high pressure carbon dioxide is filled and it is corked. That's why, so why it is you can say filled at high pressure, so that it should dissolve in the liquid. It should dissolve in the liquid. Okay. Then when you will open the bottle, that excess gas will come out. Then there will be also equilibrium, means carbon dioxide is dissolved in liquid. Then when you open the bottle, then outside pressure is less, then and inside pressure is more. In the bottle pressure is more, gaseous pressure, and outside less, that's why it will come out. Then with the existing pressure, equilibrium will change. Okay, that's why there will be equilibrium, means carbon dioxide outside and carbon dioxide inside the liquid. Inside the liquid also carbon dioxide is there, and outside also, and at the surface, then there will be equilibrium. Then you can write carbon dioxide, this reaction, this you can write carbon dioxide gas, sign of equilibrium, carbon dioxide in solution, means CO2 gas, sign of equilibrium, and CO2 in solution. CO2 gas, sign of equilibrium, and CO2 in solution. You can express, you can write like this. This is also physical process. This equilibrium is governed by a law that is called Henry's law, Henry, name of the scientist. This equilibrium is governed by Henry's law, which states that the mass of a gas dissolved in a given mass of a solvent at any temperature is proportional to the pressure of the gas above the solvent. This is a Henry's law. It is asked. Okay. Then this I told about the Henry's law. Again listen one more time. Henry's law state that the mass of gas dissolved in a given mass of a solvent at any temperature is proportional to the pressure of the gas above the solvent. Simply, more the pressure, more the gas will dissolve. Very simple way. Pressure of the gas depends upon the how much it will dissolve, means how much mass it will dissolve in the liquid, that depends upon the pressure. Directly proportional to the pressure. There. And then I given the example of gases in liquids, that is when a soda water bottle is opened, some of the carbon dioxide gas dissolved in it fizzes out, means will come out rapidly. The phenomena arises due to the difference in solubility of carbon dioxide at different pressure. There is equilibrium between the molecules in the gaseous state and the molecules dissolved in the liquid under pressure. Okay, I have told example of gases in liquids. Okay, this amount means carbon dioxide I am talking about, which is present in the soda water. Okay, this amount decreases with increase of temperature. Obviously, you can say this amount decreases with increase of temperature. Already told you, if you will heat it, then all gas will come out. All gas will come out because they are in motion. Then kinetic energy will increase and they will come out from the liquid. Okay, the amount decreases with increase of temperature. The soda water bottle is sealed under pressure of gas. When its solubility in water is high, that time it will be high. As soon as the bottle is opened, some of the dissolved carbon dioxide gas escapes to reach a new equilibrium condition required for the lower pressure. At lower pressure, a new equilibrium, and at higher pressure, again further new equilibrium. According to the pressure, they will maintain the equilibrium. Okay, that is a less pressure means a partially pressure, you can say partial pressure in the atmosphere. This is how the soda water you can say how the soda water in bottle, when left open to the air for some time, turns flat. It can be generalized. Now I am generalizing all what I have discussed, all physical process, physical equilibrium, that I am generalizing. Okay, first, for the first case I told you already, solid to liquid. 4 cases I told you that I am generalizing. For for equilibrium between solid and liquid. Okay, solid to liquid equilibrium, there is only one temperature. Okay, only at one temperature solid and liquid will be at equilibrium, and that is called melting point. And that time pressure will be 1 atm pressure. Pressure should be 1 atm, means 1013 bar, at which the two phases, means solid and liquid phases, can coexist. Both will be there. Other temperature pressure, no. If there is no exchange of heat with the surrounding, the mass of the two phases remain constant. Heat should not means a container should be closed. If there is no exchange of heat with surrounding, then mass of the two phases, means solid and liquid, both mass will be equal, remains constant. Okay, second case what I have discussed already, that is the these things, liquid and vapor equilibria. Here the vapor pressure is constant. Here vapor pressure is constant at a given temperature. Okay, third case, dissolution of solids in liquids. The solubility is constant at a given temperature. Keep in mind. Here, third case, solids in liquid equilibrium. The solubility is constant at a given temperature. And fourth one, just now I discussed, dissolution of gases in liquids. Dissolution of gases in liquids. The concentration of gas in liquid is proportional to the pressure. That is also called concentration. Pressure is also, when it is dissolved in water, then that is called concentration. Pressure is also called concentration, 2-3 gases are mixed, then that is called partial pressure. And finally one pressure, total pressure. Suppose 3 gases are mixed, then individual gases, pressure due to individual gases is called partial pressure, and final pressure, total pressure is called final pressure. Then fourth case, for dissolution of gases in liquids, the concentration of gas in liquids that is also called partial proportional, partial pressure. For dissolution of gases in liquids, the concentration of gas in liquid is proportional to the pressure, also called concentration of the gas over the liquid. Okay. Then this I have told about the, you can say, different phase equilibria. Okay. Now generally I am going to tell general characteristics of equilibria involving physical process. Okay, this you should know. It is very, very important. 4 points are there. These are the, you can say, general characteristics of equilibria involving physical process. Then what are that? I am telling you. First, equilibrium is possible only in a closed system at a given temperature. First important point. Closed system means container, closed container. It should be not opened like atmosphere. Now every time it is open, but like a bottle, in bottle you are doing, or everywhere it is closed, then that is a closed system. That is called container. Closed container is called closed system. Then equilibrium is possible only in closed system at a given temperature. First important thing. Second, both opposing process occur at the same rate and there is a dynamic but stable condition, dynamic equilibrium. And they are in a dynamic motion, okay, but a stable condition. Third, all measurable properties of the system remains constant. All measurable properties like volume, temperature, pressure, concentration, these are the measurable properties. All will be constant. All the measurable properties of the system remains constant, means temperature, pressure, volume, concentration. Fourth point, when equilibrium is attached for a physical process, it is characterized by a constant value of one of its parameters at a given temperature. Parameters means what I told you now, all are called parameters. Temperature, pressure, volume, concentration, and entropy, enthalpy, internal energy, all are called parameters. Then when equilibrium is attained for a physical process, it is observed by a constant value of one of parameter at a given temperature. Okay. When equilibrium is attained for a physical process, it is characterized by constant value of at least one value of one of the parameters, means many parameters are there. Any one should be constant at a given temperature. Okay. And last characteristic is the magnitude of such quantities. Magnitude means quantity. The magnitude of such quantities at any stage. The magnitude of such quantities means parameters. The magnitude of such quantities at any stage indicate the extent to which the physical process has proceeded before reaching equilibrium. This is the important point again. All are the important 5 points. The magnitude of such quantities at any stage indicate the extent to which the physical process has proceeded before reaching the equilibrium. You can take more reactant, all reactant has to convert to the product. Then by seeing their condition, you can judge that what extent 30%, 40%, 50% converted to equilibrium. Not suddenly it will go to 100%. It will start from the less only 20% in equilibrium. 80% are not equilibrium. 40% are equilibrium. 60% are not equilibrium. 50% are equilibrium. Like that way, and that you can tell extent how much percentage extent the magnitude of such quantities at any stage indicates the extent to which the physical process has proceeded before reaching equilibrium. Okay, and now I am stopping only here. Next class again we will meet. Thank you.